Okay, so as I said, we are going to learn both 2D and 3D plotting in the lecture today. So let's first tackle what is 2D plotting. And by the way, you have all done this in the last few homeworks and in the last few lectures, but we have not really tackled it separately in itself. So let's try to figure out how. We all know that plot xy, if MATLAB knows some data for x and some data for y, we should be able to plot xy. But what we are going to do today is to figure out how to change the, for example, the thickness of the plot, or for example, the color of the plot, or if you're trying to plot different points, you can actually use different kind of marker styles. For example, you can use a square, you can use circles. So those kind of extraneous details, those are the things that we are going to learn for 2D plotting. So let's look at this particular example. Of course, as we all know, to plot xy, MATLAB needs to know what is x and y. So let's do that here. So x is 1, 2, and please do type away with me on your MATLAB. And y is 1 to 200 with an increment of 4. Now if I type plot x comma y, we end up getting this plot. Okay. Now let's put the plot on this side of the window. Now suppose we are trying to label the different axes. So this is the syntax for that. So once I write x label is within single quotes x. If you hadn't closed the graphical window, that axis label would directly show up on that open window. So similarly, if I type y label, you see that y shows up. So this is the most simple version of a plot. It's a 2D plot. There is a certain set of x and y values, and it just basically connected those values to come up with this line. So let's try to plot this data set. So x is 1, 5, 6, 8, 9, 13, 17. Y is 9, 14, 18, 26, 34, 42, 49. If I do plot x comma y, it got this plot. Now, one thing that we always need to be careful, under this x, how many points were there? So 1, 2, 3, 4, 5, 6, 7. And under the y as well, we had 7 data points. But suppose we again have x to be the same one, but instead of y to be this, imagine that we missed out on one of the data points. Okay, and then we again try to plot that. We get an error because it says the vectors must be of the same length, implying the vectors x and y over here, they should be of the same length. So this can be something that you might face while writing a longer code, where you see an error, you don't really know why that is, because these are so simple errors, it takes a while to debug codes that throw up this kind of errors. But you need to know whenever you are plotting something, the two arrows that you are plotting, they need to be of the same length, just like over here. Yeah, so I took a screenshot of if you don't have vectors of the same length. So this is a slightly different example. So here I have x is 0 to 100 with an increment of 2, and y is 0 to 800 with an increment of 4. And if I try to plot this, we don't have the same length for x and y vectors, because x is this. On the other hand, y is quite visibly, it is much bigger than x. So it won't be able to plot this. So suppose we have this set for x, and imagine that the final value, the initial value, and the final value for y is indeed 800. Can anyone now tell me what should be the increment that should go in there for MATLAB to be able to plot this? Do you understand my question? So
16.
we have to, can you tell me why that should be?
Because you need the same like length of vector, so you would have to, if you're multiplying your n value by 8, you'd have to multiply your increment by 8.
Okay, so basically if I divide this 100 by 2, what is the answer? 50. So basically if I follow that logic, so if I divide 800 by 50, that's the number that you ended up with, 16. So you were right. So whichever way you might think, you need to have the same length for x and y, and 16 should be the increment that should give the same length for x and y here. So let's now try to plot this. And we are right, so we do get a plot. So that means that MATLAB now has same lengths for x and y vectors. So on the final exam, I might give this kind of small 2-pointer questions where you might have to fill in the increment, or if the increment is given, you might have to fill in the final value for x and y to be of the same length so that MATLAB can actually plot something. Any question? Okay, so this is the basics for 2D plotting. Let's look at a few more things. So this is the general syntax for let me just close this and open this again. Okay, so this is the generic syntax for plot. So as of now, we are just plotting some x values and some y values. But we can also change the way the plots look like. And the way we do this is through this kind of parameters. So line specifier can control things like the color of the line, or if you're trying to plot some points, what would be the shape of those plotted points? Would it be a square? Would it be a circle, etc.? The property name can actually control things like the thickness of the line or the size of that marker. And the property value is a number that you associate with this property name to figure out how big of a circle you might want for the different points, or how thick of a line you might want for the plotted lines. So just keep in mind one thing. So these line specifiers should be within single quotes. The property name should be within single quotes, but the property value is just a numerical quantity. And we are going to look at some examples for this in a moment. So this is the generic syntax, line specifiers, and then at the end, you can add the property names and their corresponding values. Okay, so before we go into that example, this is a slide that you should almost memorize at least parts of it. So for example, if you want your plot to be of color red, the corresponding line specifier is R. Similarly, for green, it would be G, blue, B. The only one which is slightly uncommon is the specifier for black, because it has already assigned B for blue. For black, the corresponding specifier is just K. So keep that in mind. If I ask you to get something, color a plot black, the specifier should be K and not B, because B is for blue. Okay, so these are some other different kinds of specifiers. So you might want the plot to be dashed instead of one single line. So that is denoted by this. But if it is a solid line, you can just use this. Of course, you have some defaults. But if you want to have some plots to be dashed and some plots to be solid, you can use this kind of specifiers. And finally, this is the marker specifier. So for example, if you're trying to plot the different points, for example, if you want to mark them by squares, you use this one. S stands for square. So let's look at a few examples. Working with this very same example, or actually it's the other one that we did. But okay, let's go back to the other one. So we had X to be this. To be this. Just to double check, X has 7 elements and Y has 7 elements, so everything is good. Now, with plot X comma Y, you would get something like this. Now, instead of plot X comma Y, let's imagine that we want this particular plot to be of, so over here we have the default to be blue. So let's imagine that we want to have it as black. So what is the specifier for black? It is K. And let's close the bracket and see what we get. So you see that the plot now becomes K. Now let's imagine that we want to have the plot like this, but along with these different points being shown through some kind of legend. So what do we do for that? So the plot is colored black, but let's imagine that those points are to be a square. So what do we do with that? So if I just press S within single quotes, we get this. But now we have missed out on the line, because now we haven't yet specified what we need in terms of the actual plot. We are just telling MATLAB that, okay, the different XY coordinate points, they should be marked by square legends, and that's what it has done. But it hasn't yet, we haven't yet told it to connect it by line. So what do we do with that? So let's try this now. And all this thing that I'm doing is basically guided by this particular rubric. So we tried to color it K, it colored it K. And then we tried to plot it with the square legend, so we used S. But for that, it just showed the legends. So hopefully if we can add something from here, it would still show a line. So let's try that. So between K and S, let's type in S and let's see if anything changed. So it indeed did. So it got connected by this one solid line. Let's try to think of a way to make the solid line dashed. So for that, instead of 1 hyphen, we add 2 hyphen, and that's according to this schematic here. So if I press an enter now, you see that the plot gets dashed. So what exactly are we doing here? We are basically specifying the line specifiers, black, dashed, and the different points to be marked by square legends. Now there is another part to this syntax, which is property name and a property value. So what is meant by that? So for example, this screenshot that I have here, let's try to carry out exactly what it did. So I'm going to change the marker size. So I write the name of the property, which in this case is marker size. And I just try a trial number, 10. Let's see how it looks like. So this is how it looks like. Instead of 10, suppose we want to have bigger squares than that. So let's try, instead of 10, let's try 20. You see that the squares get bigger. So there can be other kinds of property names. For example, here we have something called the marker face color. So let's see what that one does. So the marker face color is to fill out those square legends that we have to mark the different points. So marker face color, and let's color them red, for example, and let's press enter now. So all these markers got solid colors of red in them. So just play around with this kind of tools and make sure that you remember, number one, this slide, what are the different alphabets standing in for. And this size is also important. Here we have the property names. For example, we have line width. So let's try out what might change if we change the line width. So here is the plot we had. So let's change the line width. So line width. And the property value should follow immediately after the property name. So let's try out 10. And let's change the line to a solid line rather than a dashed. So I use just one hyphen. So this is how it looks like. It looks kind of crazy. So let's tone it down to a smaller number from 10. So let's try 2. So see, it looks all nice now than what we initially. So initially everything, it looked like this, right? Just plot XY would give me this. That's not very exciting looking. But when you're trying to write a paper, when you're trying to do something professionally, you need to make sure that your plot looks nice and it makes sense to people who don't really understand the science. So this is how you can alter different things on a simple 2D plot. Any questions? Okay, so make sure that you remember this property names. So line width, marker size, marker edge color, marker face color. Try them around on different kinds of plots. And also remember this particular slide. Okay, so the next thing that I want to do is to show you how to fit different plots on the same plane. And this can be very important, particularly in the kind of problems that we solve, where we might have to show a comparison between different plots on the same domain. So let's see how we do that. So let's try out this very same example. And there are a couple of ways how you can plot different kinds of different plots on the same domain. So let's type in the XY values that we have here. So X is from -2 to 4 with a step jump of 0.01. And the final value is 4. And Y is 2 dot X dot to the power of 3. Why are we using the dots? Can anyone tell me why are we using the dots here?
So you can multiply by a vector.
Yes, so the X here is a vector, right? Because if we just type X, you'd see a vector. So to make sure that you multiply this particular cofactors, or you exponentiate all the elements of X with this particular factor, you need to have the dot symbol because you're dealing with arrows here. So you're right. Okay, so this is Y. If I now just plot this XY, this is what the plot looks like. Now, along with this particular set of Y values, this particular problem is asking us to develop two new sets of Y values. The second one is YP, which is 6 dot multiplied X dot to the power of 2 minus 10, and YPP is 12 dot to the power of or multiplied X. So we have 3 different sets of Y, YPP, and YPP. Sorry, YP, and YWP. Now, if we want to show all of them together, we can do this. We can just plot X, Y first, and we can just continue over here. We plot XY, and then we plot XYP, and then we plot XYPP. So if we try to plot this, you would see that all of them show up on the same same domain with the same range for the axis values. But this is really a brute force way to do it, because think about when you are trying to write a code and you are trying to plot from different parts of the code. So you don't want to end till the end to plot everything, because by then you might have lost the data that you generated in a very first step. So you want to show the plot so that all the plots can come together. So let's see how we do that. So let's do CLC here. We are going to get a similar kind of output, but now we are going to plot each of them at different steps. So let's try to write a code for this. So here, all close all CLC. We have X, we have Y. So once we have, imagine that in a very complicated code, you have figured out what are the X and Y values that you want first want to plot. Then you plot them straight away, no matter what. You don't need to wait for the other sets to be calculated. So plot X, comma, Y. And the next thing that you do is, this is a new command that you are going to learn today, is hold on. So what hold on does is, it holds on to that plane on which MATLAB is supposed to plot this X and Y. And it would hold on to that plane to plot newer values that you might calculate in other parts of the code. Okay, so let's see how this works. So hold on, but then we are going to calculate the other second and third sets of Y. So YP is this. And once we have YP, let's plot X, comma, YP, because we don't want to wait till the end to plot everything together. Now, once you have used the hold on command, you don't really need to do it again in the same code. It would still hold on the placeholders for any subsequent plot that you might want to get out of this code. So let's do the third set of Y values. This is 12 multiplied by X. And once MATLAB has evaluated that, you can plot that third set. Okay, so let's try to make this look a little prettier. So for the first set, let's color it red. For the second set, let's color it blue. For the third set, let's color it black. And let's now save this. So this is fall 2020. Let 8 code 1. Let's now try to run this. So if you can run it on your computer as well, see, this is how it looks like. So the first plot is the red one, which is this one. And then the blue one is the next plot. And the third plot is just Y is equal to 12x. So it would be a straight line because it has constant slope. So it's a straight line. Okay. Now you can add other things to this plot. For example, you can do X level. And you can do Y level. But to get the new plot with the levels plotted on it, you need to save this code and run it again. And we now have the X leveling and the Y leveling. Okay, so the new thing that you learned through this example is how to use the hold on command. So generate the first plot, use hold on, and then go on with the rest of the work. And I think the homework that would be due from today's class or the next homework, you would need to use the hold on command. Any question on this one? Okay, so I think on the lecture note, I have this, basically this code, but for this screenshot here, I wrote them down on the command window, but the logic is same as as this particular code that we just wrote. So let me take a screenshot of this code as well. So this is if you use the command window, and of course this is if you're trying to develop a code and run it. Okay, so let's move on. So this is whatever I wanted to cover for 2D plotting. Let's now move into the area for 3D plotting. And that is a little bit more complicated than 2D plots. So let's try to straight away do some examples. Okay, so over here we have a certain range for t, and then we have x, y, z as functions of t. The question is try to plot this x, y, z. Because we are trying to plot 3 variables x, y, z on the same plot, as we know it is going to be a 3-dimensional plot. So this is an example of 3D plotting. So let's see what the first steps are. So if we can work from the editor window and develop a code, we can work from the command window. It doesn't really matter. Do you guys want to work from the command window or the editor window? Anyone? Did you understand the question? Say again?
Editor, please.
Editor window. Okay. So basically the command window and the editor window, they do the same work. So the logic is going to be exactly the same. So whatever we write on the editor window, you can test them on the command window. But for this one, let's stick to the editor window and write a code for this. So the code is supposed to plot x, y, z in a 3D space where x, y, z are functions of time, t, and the t range is 0 to 6 pi, and these are the 3 different functions. So let's look at how it looks like. Okay, since we're trying to write a code, again, the first steps are clear all, close all, CLC. So can you tell me what would be the next line? We have to assign the functions to x, y, z. But before we assign the functions, what is that thing that we need to do?
We need a vector for t.
We need to assign what is t. So t is 0 to, so what, can you suggest an increment on t?
0.1.
0.1. So this is a trial number which you can always change if the plot looks too jagged. So 0.1 is the increment to 6 pi. By the way, pi is a stored value in MATLAB, and you can just quickly check this. On some programming languages, pi is not stored as a default value, but it is stored as a default on MATLAB. Okay, so the range for t is now set. So the next step would be to tell MATLAB what the different functions are. So x is square root of t. So then multiplied by sine 2t. So sine 2t. But is this correct, this syntax? Do I need to change anything over here? Anyone?
You need the array operators.
So we need to make it array operators. So we need a dot here. Do we need to change anything else? I think this should suffice. But let's look back and see if we need to have a dot operator here as well. So let's keep it like this for now. Because here basically you are multiplying 2 different sub functions of t together, and you need to make sure that all the elements are being used up. Now 2t just means that it's going to multiply each element of t with a cofactor 2 because it's a sign function, so the argument is inside. Just like, for example, we didn't need a dot over here. So my logic is we probably don't need a dot over here, but let's see if this works. But definitely we would need dots before multiplication signs or before the exponential signs. So this is x. Then let's initiate y, which is square root t and cosine of 2t. And then z is 0.5 multiplied t. So now MATLAB knows what the different x, y, z's are. The next step is to actually plot, and the command for this is shown in blue highlight over here. So it is plot 3 x, y, z. Okay, let's save this and see what we get. Okay. So if I run it now, this is the plot that shows up. So this is actually correct. If you look at my screenshots here, so this is how it should look like. Let's see what happens if I had actually included the dot signs in the functions and see if anything changes over there. Yeah, so let's try something like this: 2 dot multiply t and 0.5 dot multiply t and 2 dot multiply t. Let's save this and let's run this. So we get the same plot. So don't worry too much about whether you're missing out the dot signs. In most of the cases, adding an extra dot sign won't really change what the final graphical visual should look like, because the way MATLAB does these calculations, with just a multiplication like this, it would try to grab each of the t values to calculate the argument for sine or cosine. On the other hand, if you have a sub function of t and a sub function of t getting multiplied, you need to have the dot sign, because otherwise it would come up with a single value of this one and single value of this one, and it won't really work. So it's up to you. If you can remember these examples, that's fine. But if you don't, if you're in any doubt, you can add the dot signs wherever you think they might be. But of course, for example, if I had added dot over here, that actually is a wrong syntax. And that already shows up here. It's an invalid syntax. So of course, you cannot add too many dots, but as long as it doesn't make the syntax wrong, you should be fine. Any question on this one? Okay, and on the screenshot, I have added a few more lines. For example, you can change the labels, etc. But let's move on and look at another example. And this is actually perhaps the trickiest part of plotting. So here we are trying to plot a very complex 3D plot, and the way you do it is this. So just pay attention carefully what I'm trying to say here. So first we set up what is the range of x and y over which a plot is supposed to be plotted. So if I try to give you a visual example, suppose I'm trying to plot this particular curve. So the first step for MATLAB to know is what is that planar domain, which is this direction and this direction. What is that planar domain over which it is supposed to get that plot? So once you pass on that information, the next thing that MATLAB would have to do, gets that planar domain, but now it is going to mesh the planar domain into a number of points, and all the points align on this planar domain. And once that has happened, and that happens through this thing called mesh grid, which we are going to do an example on soon. Once it has meshed that planar domain, then it can figure out the value of a third variable for each of the XY points, and then just plot that third variable. So what it does here, for example, if you take this example, this small x, small y states the planar domain. The mesh grid XY command actually breaks up this planar domain into a grid and gives MATLAB all the coordinates on that grid. So caps XY are the coordinates of that grid. And then for this function, MATLAB is going to evaluate what is this third variable z, which is a function of x and y. And those x and y are going to come from all these grid points. And it would evaluate z at each of the grid points and try to plot that evaluated value for z. And if it can plot that, that plot is going to show up in this kind of complex topographical shape. So let's, I know it's a little bit difficult to understand, but let's look at an example. So the first things first, we need to figure out the domain over which we want to get that complex looking plot. So let's look at this particular example. So plot the following function on a 3D domain. The function is given by this 2 to the power of something times sine x times cosine of 0.5y. So it is going to be a complex looking plot, but the first thing, when you see an example like this on the final exam, the first thing that you would try to figure out is what is the range of x and y over which we have to plot this. And that is clearly given to you. X should be between -5 to 5, y should be between -5 to 5. So let's try and write a code for this. So clear all, close all, CLC. So the first thing is, what is the domain for x and y, the planar domain? And x is -5 to 5. So let's try an increment of 0.1, and we can change that later on. So this is the range for x. This is the range for y. So -5.1 to 5. So once that planar range is set up, now what I just said in that other example is you have the planar range, you have to break it up into grid points. And you do that with this particular MATLAB command, which is mesh grid. And mesh grid x, comma, y. So what this is going to do is, sorry, this red sign is coming up, so something is wrong. So it should be actually regular bracket instead of square bracket. So what mesh grid does is figure out the coordinates of that grid that you have laid on that XY plane. You want to associate those coordinates to a certain set of variables. So let's those variables be capital X, comma, capital Y. So what this capital XY would have are the coordinates for different grid points on that planar 2D surface. Now, once we know those XY values, we just need to plug in these XY values into this function, which is again a function of XY, to figure out what would be the value of Z for that grid point. And then the value of Z would vary at different grid points because the XY values are varying, the capital XY values are varying. So it would find different values of Z at different points and then try to plot it, which incidentally is going to look like a very complex topographical plot. So again, the first step is the planar range. The second step is getting the grid points and assigning the coordinates to a certain set of variables, which in this case is caps XY. The third step is actually figuring out the function that is to be plotted, which in this case is Z. So Z is, let's type out the function that is given to you. So 2, then dot to the power of minus 1.5 dot multiplied square root x dot to the power of square plus y dot to the power of square, because the small x, small y, they're all arrays over here. See, when I exponentiated this too, everything is within a pair of brackets, so I arranged it accordingly. And what else is left? We have sine x, so dot multiplied sine x and dot multiplied cosine 0.5 dot multiplied y. So this should give you the function. And let's now plot this. So plot. Now I have two questions for you guys. XY, the plane, and then figuring out the grid points, which are capital X, capital Y, and then trying to evaluate what is the value of Z for each of those capital X, capital Y. Can you tell me if there is an error in this line? Here we are trying to figure out the value of Z for different capital X and capital Y. Anyone? Can you, do you think there is an error on this particular line? Okay, in that case, let me rephrase my question. Here I have used small x, small y. Do you think this should be small x, small y, or do you think this should be capital X, capital Y? Anyone?
Aren't they the same numbers? Does it matter?
It would matter, because when I state what is small x, small y, that's just the planar domain. On the other hand, these are the grid points that will be used to evaluate the function, which is Z over here. So this
Big X, big Y.
This should be, yeah, you're right. So this should be capital X, capital Y, because that's the exact reason why we did this step. We want to have a set of XY points on that plane and then use those XY points to figure out the value of Z for such values of X and Y. So this is a very common mistake, which I myself do sometimes, but make sure that when you are trying to find the third variable, that is actually dependent on the variables from the grid points. So that is the first step. Now let's try to plot this. Now, plot is not the command that we are going to use for this kind of problems. The command for this is actually mesh. So mesh X, Y, Z. Make sure that these are capital X, capital Y, because those are the points that you are actually using to get that eventual plot, not the small x, small y, which was just to figure out what is the range for that plot. So let's try to save this and see what we get. We might need more work on this. So fall 2020, let 8, code 3. Okay, so if I run this now, this is what we get, which looks like the example that we had. Now, this just shows you the mesh, and by mesh, it basically means a network. If you want to have a surface plotted over here, the command for that is surf x, comma, y, comma, z. And if I save this, if I run this, the corresponding plot would look like this, where that mesh has been overlapped by a surface which lies along the same topography. Okay? So make sure that you understand this particular example, and this screenshot is given to you. The basic idea is this: find the planar domain based on what is stated to you in the problem, then develop a grid on that planar domain to find out the coordinates of each of the grid points, which in this case is capital X, capital Y. And then the third step is plotting or evaluating the third variable, which is Z in this case, because we are talking of 3D plots, so there has to be a third variable, which is z as a function of the grid points, grid point coordinates, capital X, capital Y. And also make sure that you remember the syntax. So this is regular bracket here after mesh grid, but when you are trying to store those points under caps X, caps Y, it should be a square bracket here. Okay, so try to write this code out, and you can change this. You probably don't need this complicated of function, and you can try to come up with different kinds of odd-looking functions. But try to understand the logic over here, which is slightly more nuanced than just getting a plot on MATLAB. Okay, so try out this example here. Actually, there is an error. The error being the array operation was not done correctly, as you can see in the screenshot. So of course, if you don't find the plot that you want to find, and you get something which is not really looking right to you, that can be a possible reason that you have missed out on some of the dot operators. So make sure that you don't do that in the homework or especially in the test. Okay, so this is another example which is not very important, but I just wanted to include this, that you can draw pie plots as well on MATLAB. So for example, here I have studied the populations in millions in different continents, and then the continent names are here. So if I just use the syntax pi3 and then the population numbers and then the continents, it would develop a plot like this. So please do try this particular code out as well. But the most important thing from the lecture today is understanding whether you can figure out the logic over here and how to get this kind of complex topological plots. So if you look at the homework, there's just one single problem. It's on this particular concept on using mesh grid and then mesh and then surf. So work through the example that we did in class to figure this out. And if you have questions, ask that here. And for your midterm, I have not yet started grading. I might not be done by Thursday, but I definitely do plan to get the scores back to you by next Tuesday's class. Okay, any questions? Okay, sounds good. So I'll see you guys on Thursday.